Today we will talk about inner product spaces, which is also known as Pre-Hilbert spaces. Before passing to that, let's talk about the inner product itself. So, actual inner product is kind of natural extension of the scalar product that we are familiar from undergraduate courses. Let's look at the definition of that. So, here is the definition of inner product for the vectors given from this space. K can be a real number space and complex. So when we have a K is equal to R, then it's a usual scalar product, but when we have a complex, then it's called standard inner product. So this idea can be carried to in function space. C stands for continuous, so continuous function space defined on a b interval. So for the given any two functions from these spaces, we can define this inner product in this form. But for this to be inner product, we should satisfy the following properties. So for a given A vector space, remember that our function space, continuous function space, is also a vector space. This can be easily proven. So for a given bilinear mapping, all this should satisfy. First property is sesquilinearity. It's kind of generalization of linearity. Second is symmetry. Fourth is positiveness, and the last one is definiteness. So when we have all these are satisfied for our defined inner product, then we call these spaces as inner product space or Pre-Hilbert space. So now let's prove for our defined inner product all these properties are satisfied. So now we have this. So let's first prove the sesquilinearity A. Sesquilinearity. Okay. So what does it say is this. So when we have this equation, for a given f, h, and g functions from function space, we have this equality. Okay, so it's kind of straightforward, even though let's do it now. So we can write this in this form, a and mu g as h multiplied by h conjugate. So since our function space is also a vector space, then we have a linearity, and we can expand this in this form. Without any doubt. Okay. So now we can continue this, and it directly comes down this form. Pardon, I forgot here conjugate operator. So now we proved the first part of sesquilinearity, but there's a second, and it can be also done in a similar manner. So next one is a symmetry. Okay, so let's continue here. Now we know the definition of inner product. We have this and multiplied by G conjugate. And so before passing to that, let's write f in this form plus this real. Let's separate f into real and imaginary part, and also let's separate g function. Pardon, I forgot here putting the I. So we separated f and the g functions into real and the imaginary parts. Okay. So now if we continue, we can put this form into the equation here. Since it's a conjugate, we have here minus value. Yes, so then this, once we do all calculations here, pardon, expansion of brackets here, we will come up with this form. Okay, so real parts, let's write first real parts. Pardon, it should be f plus the complex part, imaginary part of the equation. Okay, and minus f imgen. Okay, now let's keep this in mind. Now let's look at the second part of the right hand side of the equation, so which is this. Okay, so now we have this whole conjugate, then we have this. Okay, again if we expand this, we will have something similar, actually exactly something exactly same as above, but let's verify it. Okay, again real part and imaginary part of g function multiplied by, pardon, as of now we don't need it. Okay, so okay, again if you expand this, you will see we will have exactly the same thing as before. So we conclude from here that we have a positiveness property satisfied for the defined operator, for the defined inner product operator. So now what is left is, pardon, we were talking about the symmetry. So now let's talk about the positiveness. This. Okay, now let's continue from here. Let's say again we have the same function, then we have this, and we can write in this form from the definition of the inner product. Okay, so actually this is straightforward, and since it is always non-negative, then whole integral is non-negative. Okay, since it's whole non-negative and then whole integral is non-negative, so we are done with positiveness. Now definitiveness. So we should prove that when we have a zero, actually when we have equality in the positiveness, then actually it should show us that the function itself is zero always. So before proving that, let's take a look at this lemma here. Okay, so basically it says when we have a continuous function, non-negative continuous function, and having satisfying these properties, this property, in other words, take an integral in a and b, a b interval 0, then function should be also itself 0 everywhere. So to prove that, here author says that let's take any point from t dot from this interval. So first let's start with contradiction. So we say that if f is not equal to 0 always, then we can find the point t0 element of AB open interval such that this is not a 0. It's obvious, and it's greater than 0 because we have always non-negativity. Then since function is continuous, by definition of continuity we can write in this form. And let's look at this integral. Now we have this integral. Since this t plus minus is subinterval of AB, we can write in this form. We have this inequality, so we are decreasing the value, and the plus, we know that this function is always non-negative. Thus, when we take the smaller integral in smaller interval, we will for sure have a smaller value in total. Then we have this equality satisfied. Then if we put the epsilon in instead of f, then we will have this, and since epsilon and the sigma greater than 0, then we have always greater than 0. Then this contradicts the hypothesis. So what this lemma says is that when you have a continuous function and the non-negative continuous function, and if it satisfies this, then it's always 0. The function is always 0. So now let's return to the last property. Okay, so inner product is called definite when it satisfies this. So now let's look at how we can use this lemma and how we can prove that our defined inner product is definitive. Actually it's straightforward now. Okay, now so it means actually from above we see that we can write in this form. Okay, then now f square absolute value square is actual continuous function defined in AB interval, since f is continuous and defined in this interval, plus since there is a square, it is always non-negative. Thus from that lemma, and we have this 0 from here, thus since we have this from that lemma, we have always this equal to 0. This leads to f equal to 0. This leads to f equal to 0 because f squared actually is equal to per real part square plus imaginary part square equal to 0. From here, separate the real part of function is equal to 0 and imaginary part of the image equal to 0. From here, we know that f is equal to 0 everywhere. Okay, so now we proved that the inner product that's defined in this form is actual satisfies these all properties, and it is a inner. Then we can call it inner product plus, and the space that is endowed with this operator is called inner product space, also known as Pre-Hilbert space. Lastly, these screenshots or these definitions and lemmas are taken from the book that I will put in the below of the video. If you want, you can take a look for the detailed or further explanations. Thank you for your attention. Bye.